Hello everyone. Today we are going to discuss about the RLC circuits. These kind of circuits are very important when we are designing oscillators, filters. So before go through those circuits, we need to first understand the operation of the each RLC circuits. So we have mainly three RLC circuits. First, RC. So to build the RC circuit, we need resistor and capacitor connected in series or parallel, depending your circuit conditions. And then we need voltage source. Here we have voltage source and R and C connected in series. And second one, RL circuit. So similar to the first one, we need R and L component connected in series. Either we can connect it in parallel also. And then we need to give some supply power by using voltage source or current source. Last one, LC circuit. So in here, we have to connect L and C in parallel or series. Similar to the previous two circuits, we also need some supply voltage to give the power. So let's go for some application. So it will be very good for you guys to understand what's going on. So here is the application of RLC circuit. Mainly, we have two applications, oscillators and filters. Regarding the oscillators, we have different kind of oscillator. We can design, we can develop the oscillator by using the RLC theory. So in here, we have a stable multivibrator. When we derive the equation for this oscillator, it gives some differential equation. So then by using that differential equation, we can calculate the frequency. And here, this is the phase shifting oscillator. This also use R and C. In here also we have used R and C. In here, we have relaxation oscillator. In here also we have used R and C. There are so many oscillators that also use different kind of configuration. Similar to what I discussed at the first slide, we have RL and LC. Then we can go to the operation of the RC circuit. So in here, we have two schematic. The condition is S is open, which means this is the mechanical switch. We can manually open this one, okay? To control the circuit, we can manually open or close. In here, we already open this one, then there will be no current to charge the capacitor. So then we can say the initial condition of VC equals 0 because there are no current. So when it's come to this figure, so now we have closed the switch, which means there is the current called IC that can flow through the R and C, then finally end up with the ground. By using this configuration, we can express some equations. First, IC. How did I get that? First, I need to give the voltage difference. We know that the Vs is always greater than Vc because Vs voltage source provides the voltage. When the current goes through this line, the voltage can be continuously degrade through the line. Okay, so then we can get the voltage difference by using Vs minus Vc. Then we can obtain the current after dividing the R here. So then now we have the current. As we know, we can also obtain the capacitor charging current. It's typically given by the IC dV over dt. I means the current, C means the capacitance, Vc means the voltage, T means time. After obtaining these two equations, we can let them to be equal. So then we can separate the variables. See, in here variables is Vc. So Vc divided by Vs minus Vc. Here is the variable. So be careful, Vc is constant, Vs is constant, okay? Rc and also constant. Only variable is Vc. Now I have separated the variable. So this expression equal integrate that goes to 0 to t dt over rc. Rc is constant, which this constant we call time constant. After integrating this one, we can add the limit. So 1 over x, when we integrate the 1 over x, it gives the ln x. In here, 1 over Vs minus Vc. Minus Vc, then the minus ln Vs minus Vc. This is we call the absolute value, okay? Because the inside the ln cannot be minus. So then the limit goes 0 to Vc, then equal, since in this terminal doesn't have any variable, so just t, okay? So then just t divided by rc. So in here, we can easily move the minus sign to the right side. So in that case, we have minus t divided by rc. So after adding the limits, we will have this subtraction, okay? So then we know that according to the logarithmic laws, the subtraction we can change to the dividends. Okay, in here we have dividends. So then the positive one goes up and negative one goes down. So here is the dividends that equal the minus t over RC. So then we can get the anti-ln. So which means that we can remove the ln, it gives the exponential function. So here we have the answer. So variation of VC equal Vs bracket 1 minus e to the power minus t over RC. So this is the variation of VC. So it is correct. Once we close this switch, this capacitor start being charged. Here starts being charged. It starts from 0, then it end up with this voltage. Okay, and this voltage, it is like V. In here Vs. Okay, end up with this voltage. In here they mention just the coulomb, it doesn't matter. So now we can also obtain the current, the IC current. What we need to do is we just need to differentiate this function by dt. So in here, once we differentiate by dt, we will have this expression. See, Vs of R e to the power minus t over C. We know that the dimension is correct. Vs divided R in I. So now we have two expression for the VC and IC respectively. So you need to derive this equation by yourself to get the better understanding. So now we can go for the very special cases. We have two special cases. What happened in here? The time is also become RC here. RC. So we have in here minus 1. So 1 minus e to the power minus 1. The answer will be VC equal 0.63 Vs. So then also, so we can get the condition. So what happened? What is the time duration when VC become half of the source voltage? When the VC become half of this voltage. So to do that, we need to replace the VC by Vs divided by 2. So then after solving this expression, we can obtain the time will be T equal RC ln 2. So this is the time. Now we can go for the RL circuit. Similar to the previous one, in here also we have two schematics. First, the open condition, second, closed condition. When the circuit is open, there will be no current. Current is 0. In that case, VL is remaining at the 0. When the switch is closed, there will be some current that can flow through the R and L. Then the inductor is being charged. So now we can obtain the IL. So IL, how we can obtain the difference of Vs and VL divided by R, similar to the previous. Now in here, we can apply the condition for the inductor. In that case, we know inductor voltage equal, the voltage across the inductor equal L DIL over dt. This is standard equation. So you can further find out through the Google. So then we can add this VL with here. So we can add this VL into this one. So after that we will have IL equal Vs minus L DIL over dt divided by R. So after separate the variables, we will have this equation finally. So DIL divided by Vs over R minus IL equal R divided by L dt. So this is the integration equations. So now we can integrate 0 to IL and 0 to T. So after that you can obtain this expression. Very easy. So now we can remove the ln by using anti-ln. So then you will have IL equal Vs over R times 1 minus e to the power minus RL R divided by L time T. So then what we need to do is we can again differentiate by T to get the VL. See, after differentiating this equation, you will have Vs e to the power minus divided by L times T. See, this is the variation of current. This is the variation of voltage. This is a function of current. This is the function of voltage. So here the current is being charging and here discharging. The charging, discharging. This is the inductor current. Is being charged. Then after that it can discharge. Now let's talk about the LC circuits. LC circuits are little complicated compared to the RC and RL circuits because LC circuits give second order differential equation. Here is the schematic of the LC circuits. Similar to the previous circuit, I just use the voltage source for powering, and here I have used inductor and capacitor connected in series. In this case, the switch is open. Then there is no current passing through the circuit. Then the VC remaining at the lower value, which is 0. Once the switch is closed, there is current, IL current, that can pass through the circuit while charging this capacitor. Then we can obtain the voltage across the inductor, which is given by Vs minus VCL DIL over dt. And also we can obtain the accumulating current into the capacitor, which is given by IL equals C dVc over dt. Then the second equation can be added into the first equation to get the second order differential equation like this. Before solving the second order differential equation, I am assuming that the genetic sign function, which is given by this equation. So after adding this genetic equation into the second order differential equation, I can finally obtain the value for the omega, which is given by omega squared equal 1 over LC. So now I can add this omega into this genetic equation to obtain the VC. This is the expression for the VC. And also I can get the accumulating current into the capacitor by differentiating the VC by dt. Then finally I will have this equation. So here is the two waveform related to the VC and IL. So here is the RLC resonant circuit. This RLC resonant circuit will be more complicated compared to the previous circuit. But the important thing is when we have the LC circuit, it doesn't matter due to the conductive resistance of the copper inductor and wire. It also like the RLC circuit because in here now the R like the parasitic resistor. So in the next video, I'm going to discuss about the RLC resonance circuit. Thank you very much for watching this video.